Hello, everyone. Welcome to next TSVP seminar. And first of all, this is the youngest audience I ever saw in OIST. So I think we should invite all high schoolers to all the seminars at OIST. That looks great. Great, welcome. Great. And well, it's my pleasure to introduce our speaker, a young scholar, Professor Havva Yoldas, and she's visiting Okinawa Institute of Science and Technology from Delft University of Technology. So she received her PhD in 2019 in Spain from Granada University and Basque Center of Applied Mathematics. Then she had a postdoctoral fellowship she was a CNRS postdoctoral fellow in France, Lyon, France, right, in Camille Jordan University. And then since 2022, she took the position tenure assistant professor in Delft University of Technology. So her expertise is she's an expert in the field of working in the field of analysis and partial differential equations. And she is specifically looking to questions of well-positiveness and long-time behavior and asymptotic qualitative properties of solutions of partial differential equations which arise in applications, something like population dynamics processes, chemotactic, coupled reaction diffusion systems, like chemotactic systems. And today's talk is as it's announced, it's mathematical modeling across scales, from microscopic to mesoscopic and to macroscopic. Please.
Is it on? Yeah, thank you very much for this nice introduction. And thanks a lot, first of all, the TSVP for hosting us very nicely here. And thank you all for coming, and also the high school students. Yeah, so I will try to try to make it accessible as possible, but we will see. So today's plan, So today's plan is this following. So I would like to give you an overview about mathematical modeling across scales, particularly focusing on an example, well-known example from physics, right? And maybe briefly mention the motivation in the area. And then I will show you a little bit of like some pictures, movies, where else we observe this kind of thing in nature. And then last bit, I will try to give 3 examples from my own research, different models in different scales, and try to introduce them. They are very different. One of them is really like the chemotactic bacteria movement. The other one is how elongated particles align with each other. And the last one, I don't know if there will be time, but I thought it's an interesting problem. So it's gang interaction dynamics. So yeah, let's start. So when I say multi-scaling or modeling across scales, I mean the following. Here we have a diagram. In the x-axis, we see space, and the unit is meters. And in y-axis, we see time, and unit is in seconds. So if I ignore for a bit the relativistic effects, the physical phenomena can be classified or modeled in this 4 physical scales. So the smallest one is the quantum scale, right? Where you see one Armstrong, the space, and 10 to the power minus 15 is the second time. So this is the smallest scale. Then we move to a bit larger in space and longer in time, right? We have the molecular dynamics, classical mechanics. That is the microscopic scale. Today, I will be mentioning these 3 scales, not the quantum one. I'm not focusing on there. So this one is the microscopic scale. And here, I jump into macroscopic scale. That's the scale actually we observe the things around us. So the unit is meter and then seconds, right? These are the things we observe, we see every day. And in between, there is this kinetic scale, which is mesoscopic scale, where it's like in between really these microscopic and macroscopic scale, but sometimes it helps us to understand phenomena and different properties. Like it will help us to recover different properties of the same matter. So let's carry on. So what I mean, so here we see a glass of water, right? So what I just mentioned can be summarized as the following. So I would like to make a mathematical model for this glass of water, right? So I can zoom in really, and in the first picture, I can look at it in the microscopic dynamics. So I can really zoom into the molecules of water, right? So I go back, little zoom out, then it's the mesoscopic scale where I reach is the kinetic theory. And in the macroscopic scale, the scale that I observe the water, right? Like it's just in front of me. And the example that I would like to give here is the following. The first scale, the microscopic scale, we have the Newton's equations for motion, right? We have the particles, they move and then they interact with each other. In the second one, the second scale, the same phenomena can be modeled by using Boltzmann type equation. So that's a kinetic equation. I will come to that in a bit. And the third case, I will have the Navier-Stokes equations or Euler equations that I use in modeling the continuum dynamics or hydrodynamics, right? Water or any fluid, right? So I will tell you a little bit about how can we connect these three scales mathematically, or what do we do to connect these things? How can I derive Boltzmann equation from Newton's equations or Euler equations? Okay, of course, I will not go into derivation in detail, but I hope to give you some overview and would like to tell you why it is important, right? Okay, so first, we have considered that we have like a particle system, like with n particles and finite particles. Now I'm looking at the microscopic scale, right? So each particle, so this is the equation for particle number I. So x shows its position and the time derivative of x is showing its velocity, right? So first equation, these are Newton's equations for motion, right? Second one is giving me the time derivative of the velocity, and it goes according to the force term, which is given the minus of the interaction potential here, phi. So that is the sum of all the force exerted on particle I by all the other particles, right? So this is the model I can use in this microscopic scale to model this dynamics. So I would like to connect this to mesoscopic scale. So what do I need to do for that? So first of all, you saw in the picture, I need to consider many number of particles, right? So n will be very large in that case. So I will try to send n to infinity. So I would like to have an equation for big number of particles. So to do that, what I first do is that I describe something called probability measure. So it's a statistical quantity. So I have now many particles. I look at one place in space, and I look at actually the probability of number of probability of particles occupying that space in x in with velocity v, right? Now I show my phase space at z, and it consists of the locations, positions, and velocities of my particles. So, luckily, I mean, this probability measure solves a well-known equation, which is called Euler's equation. So I will not go into detail, but it's just to say that the in time, this probability measure evolves according to this dynamics, right? Here is the force term, and force term is really equal to minus of the potential energy you can think of. Okay, so still I have n number of particles. I have a probability measure, but still big number of particles. I still have the problem of sending to infinity, or I would like to I would like to say something about the average behavior of this statistical quantity. So to do that, what I do is that I take an average on this probability measure, right? So I sum them up, I take an integral, and now new unknown j of n there is a probability density function, which is giving me the probability of finding a particle at time t at position x moving with velocity v, right? So this is my now unknown and variable. So I'm still not there yet. I would like to send this. I still have n of these probability density functions, right? I would like to get an average behavior. I would like to get rid of n, right? That's my goal. So for that, I need to make some assumptions. So first of all, if my particles are not identical, it's kind of impossible for me to get an average behavior, right? So what I need to assume is that these particles are identical, and I call their radius, I call them, like, you can consider them as small balls, right? The radius epsilon, which is a small number. Okay, so I need to also make some assumptions on how they interact with each other. So yeah, one of them is like here in this case, since I would like to reach the Boltzmann equation, what I need to make is that, like, they collide with each other, right? The gas particles here, they collide and they change their velocities, and they change their directions and keep the momentum conserved, right? So for that, I need to assume that velocities before and after collision, they are uncorrelated, they are not related. And if I need to look at some small subset of a space where I would like to, by looking at this part, I would like to get an understanding of the whole behavior of the system. For that, what I do, I confine all these particles in a box, okay? So in a box, if I send my number of particles to infinity and the radius to 0, so if I take them smaller and smaller, I actually put in this box an infinite number of particles, right? This is actually what I would like to have, right? Something like that. So that's precisely, I assume. And here, this means that n times epsilon square is a constant number. So that's some important number. It's related to Knudsen number, which will come later. So under these assumptions, since I considered some epsilon scaling the radius of my particles, second equation in the Newton's laws of motion become like this. So I modified it a little bit because of this epsilon consideration of my particles, right? So now my Newton's equations are in the following form, right? Then I'm doing some limiting processes, sending n to infinity and epsilon to 0 under these assumptions that I listed. What I obtain is the following equation. This is called Boltzmann's equation. So this, Raphael had a talk 2 weeks ago. We had a talk on plasma physics. So this was mentioned a bit. I will not go into so much in details. So this is the equation we obtained. So this shows you the time evolution of the probability density function of finding a particle at time t at a space x moving with velocity v. So this time evolution is in the first term, so time derivative, partial derivative of f. So this f function depends on time, space, and velocity. So it's not written there, but maybe better to write. Right? So I'm skipping the dependency. Yeah, it's written, okay. Yeah, so the second term is giving me the free transport. So it is the movement with constant speed, right? And the right-hand side, in this Q functional, which I did not detail, it gives me how the particles collide, which for now is not very important. And K is a small number, it's Knudsen number. So it's some constant related to mean free path. So it means the average time between two particles collide, and some characteristic length scale. So this is not very important at this stage. So this is the equation Boltzmann came up for modeling the rarefied gas. So rarefied gas is like gas you can find maybe after you go to atmosphere a bit. So it's like very low density gas. And it's a correct model. But rigorous proof of this derivation was kind of open until very recently, which I will mention. So what I would like to go to from here is that what happens if I take a different scaling? So I assumed for the Boltzmann derivation at some point, n times epsilon square is a constant, right? instead of epsilon square, I take a different scaling, and n times epsilon cube is constant. So what happens is that then instead of second equation was like this previously, instead of that, you will have this type of equation. So here, square root of epsilon. So you may think that this didn't change so much, but then when you take a limit, actually, what you obtain is a different equation. It's a Landau equation for plasmas that was mentioned 2 weeks ago also. So it is an equation for more dense gases. So do you know what a plasma is? Right? It's like a star, right? Sun is plasma, or lightning is a plasma. So those are like denser gases than we observe. So that's another equation, right? So what I'm trying to say is the scaling that you take or assumptions that you make are very important here for the equations that you obtain. Okay, so now I'm at the mesoscopic scale, kinetic scale. I have the Boltzmann equation, and I would like to go to hydrodynamic scale, macroscopic scale, right? So how do I do this? Is that I would like to increase the pressure, right? I would like to consider more dense substance, right? Like, so I want to squeeze my gas even more than like a box of gas, let's say. So it should behave like a fluid. And this corresponds to sending this K to 0. Okay, sending K to 0. So first, to be able to define my equation, I need to define some macroscopic quantities. So these are local density. It's not very important, so don't get scared if you are seeing this for the first time. Local momentum, so density depending on time and x. So the velocity variable is lost now. We are like getting rid of it. And the second one is momentum, local momentum, and the temperature. So here, at this stage, the assumption that I need to make is that total density, momentum, and the energy temperature are conserved in time. So these are called conservation laws. So under these assumptions, I can obtain equations for these quantities for density, momentum, and energy. So we, again, don't look at it. So it may be looking scary, but it's not. So from there on, adding additional assumptions, I can reach to hydrodynamic equations like Euler's equations or Navier-Stokes equations. Okay, so this is the process that maybe I can summarize the process in that way. I will not go into more details. Now I will try to give different examples. But as mathematicians, we try to make every step of these limiting processes rigorous as much as possible. So that's what we are interested, let's say. So if we go back to the bigger picture here, which the one quantum scale that I didn't mention, there you have the Schrödinger's equation and Newton's equations, Boltzmann in the kinetic level, and fluid equations, Euler's or Navier-Stokes, right? So these 4 equations actually describing the same thing in different time scales or time and space scales. Okay, so why this is important? So maybe you have heard of a mathematician called Hilbert. Do you know who Hilbert is? So he's a German mathematician, and in 1900 he published 23 problems that they were unsolved, they were not solved at that time. So this is actually connected to 6th problem of these lists, 23 problems. So 6th problem is like, this is like a quotation from there. I don't want to read it all, but it points out the need to rigorous derivation of these, connecting these different scales. So this is still an open problem. So still, I mean, in August, there was a preprint where the authors, they are deriving for the first time, for longer times, the Boltzmann equation from Newton's laws of motion, right? But from Boltzmann to Navier-Stokes or Euler's equation, it's still an open problem. So it's a big open problem in the area. So many people in my area working on these kind of things, they are trying to contribute in solving this big open problem by Hilbert. Yeah. So this is the motivation. And what I would like to talk about a bit is that actually you can do very similar limiting process for models coming from different areas, from biology, ecology, or social sciences, even chemistry and stuff. So the examples that I would like to show now from those different disciplines, let's say. And so before that, I would like to show you how you would observe it in nature, right? Collective behavior. I will show you a couple of examples from swarming models. So this is a picture of sheep, herd of sheep. And you can see how you can individually like locate these sheep, right? But also when they are packed, you can consider them as a fluid. So there are very nice videos. If you check YouTube, you will find, but because of copyright, this is the picture I put here. So same example, similar example, you can observe, of course, also flock of birds, right? So this is, again, you can find more spectacular, more resolution version of this, but again, for copyright reasons, this is the one I would like to show. So you see these birds are like particles, but when they get aligned together, then they behave like fluid. So the fluid equations can also be used to describe the behavior or movements of these type of birds, let's say. And the last one in this similar manner is the schools of fish, right? So for this one, this is the photo that I took last week, so it's copyright free. So it could be better. So again, you can find denser flock of schools, so a school of fish, let's say, but this is the one, yeah, maybe less dense area. They nicely align with each other, right? So these are some of the examples where we can use this procedure to model this type of behavior. Okay, so here, let's see the time. Okay, I have 30 minutes. Now, I would like to give 3 examples. Yeah, okay, so first, maybe let's wait for high school students to leave, I guess. Yeah, I see the sign. So first example that I would like to give from my research is this kinetic model, run-and-tumble model for bacteria movement. These bacteria are chemotactic bacteria. So E. coli, I will mention later. So I will, towards the end, I will summarize the results which I obtained with Jo Evans. She's from Warwick, University of Warwick in the United Kingdom, from these papers. Okay, so how do bacteria, chemotactic bacteria, move? So what they do is, here is a cartoon of it. Here, this like sugar crystal in the middle. So it's not an experiment, it's just a cartoon, right? So what they do, the bacteria, they have like, it's a combination of 2 different movements. One of them is like straight, they go in a straight line with a constant velocity, and then they tumble. So they randomly change their orientation to find food source. So towards where the chemoattractant is, right? So in this case, like they are like getting accumulated towards this sugar crystal, right? So it goes back to, yeah, it goes back to these experiments. They discovered, they made like some experiments on E. coli, the bacteria, which is, I guess, easy to find, and they found out that it is like oxygen and some sort of sugars. They are they behave as chemoattractant for these E. coli. Okay, so what some other properties of this model is that, for example, so this is the same thing in simulation on MATLAB. I'm just tracking one of them. They are supposed to be like a bacteria, right? So this is the chemoattractant gradient. So it is like the red part is where the density is highest, right? So what they do is actually, when they move away from the high dense chemoattractant regions, they tumble often because they would like to change their orientation, and they try to find the food, right? And when they are going towards where the chemoattractant is higher in density, their runs are longer. They don't tumble much. So you see here, so this one is going towards where the chemoattractant is higher, right, the density. It runs longer time, so it goes in constant speed. And then here, notices that it's going wrong direction and just tumbles. So this movement is happening. There is some randomness in this as well. So yeah, they perform biased random walk, let's say. Okay, so before coming to the model for that, I briefly would like to show you this gentleman. Anybody knows who he is? I mean, it's written who he is, but do you know what he did or what he found? Anybody maybe working on bacteria-related stuff? Maybe not. So he's the one who person who discovered bacteria for the first time. And why I would like to put the picture here, because he lived in Delft, so that's where I'm working at. Okay, so what he did is like, he's not a person who went to school or anything. He's like self-taught person. He made some microscopes, and with those microscopes, he started looking at everything he sees, right? Then he noticed some stuff like small particles, like some small things that they move. And he called them animalcules. Meanwhile, people were talking about molecules, so he got inspired and he called them animalcules, and he sent his findings to Royal Society in London, I think, like in a couple of letters. So I also wrote a couple of more names. This Hortberg, he was a physics professor. He worked a lot on E. coli. So he has these small, like YouTube videos, like maybe half an hour each. He explains like the history and everything very pleasantly. If you are interested, you can go and check those. And yeah, so this is the guy who first observed, like found, like, let's say, discovered bacteria. And yeah, after this small history, I'll go back to my model again. So what Adler did in 1966 is that he considered a long tube, and he put one end E. coli and the other end oxygen or galactose, some sort of sugar, and he observed what happens. So this is the tube, right? Here's the end where the bacteria are. And in time, what happened? Bacteria just moved towards oxygen, let's say, right? And it also formed bands. So these are, sometimes we call them traveling wave bands, these are, right? So they got accumulated here and there. Okay, so in a microscopic scale, we can look at this as each bacteria, we can try to track their position and velocities, like, right? And in the mesoscopic scale, which I will be focusing on from now on, you can also model them with an equation, Boltzmann-like equation, which is called run-and-tumble equation. Or in the microscopic scale, you do certain limiting procedures and you obtain a macroscopic PDE system, in this case, Keller-Segal system, because those were the guys who first came up with that. Okay, so here is another experiment of traveling wave bands. Here, the red ones are where bacteria is high in density. And so let me show you the equation. So run-and-tumble equation is this one. So here again, I see, you can see on the first term is the time derivative of my f. F is again a probability density function, this time of finding a bacteria at time t at position x, moving with a velocity v, okay? So again, I have the run, like this free transport. Second term is describing the free transport, that's basically the runs. And right-hand side is describing the tumble events, which maybe is not very important for now. I didn't write it explicitly what it is. This T has different terms. And what I take is that velocities are, post-tumbling velocities are taken uniformly from a ball. So then I take my velocity space as ball with radius v0. So T describes the change in velocity from, in this first case, v to v prime, in the second case, v prime to v. So before before tumbling, the bacteria they have velocity v and they change it to v prime, right? The ones which has velocity v, I take them out of my system, and the ones which they will have the v prime velocity, I put them in the system. So it has loss and gain term. And one thing you notice is that it looks very similar to a linear Boltzmann equation, or sometimes called as BGK equations. These are three physicists. Since Boltzmann equation is very complicated to study, people came up with toy models, and these three physicists, Nagar, Gross, and Crook, I guess, those came up with this type of model. So it resembles to this, but still there are some differences. So before that, maybe I will talk a little bit about general problems mathematicians find interesting in these type of equations. So this first one is like a general form of kinetic equations, where I have T of F is my transport part, and right-hand side, C of F stands for collision, my collision part, okay? Collision part is different for every different model, because everything interacts in a different way, right? So what I'm interested in here generally is that when I see an equation or a model like this, as a mathematician, I would like to show that it's a well-posed model. So what does that mean? It means that there exists a solution, and that solution is unique, and it depends continuously on the initial data that I took. So when I say existence of solution, then I need to define a notion of solution. So there are different notions of solutions that I will not go into detail, but they depend on the properties, mathematical properties of that probability density function, or in general, my unknown. So if it's a probability density function, it's something nice already. So once my model is well posed, what I look at is what happens in long time. As time goes to infinity, can I find an equilibrium or steady state for this unknown f, right? So I denote this as f infinity. So as time goes to infinity, my solution converges to something which does not change in time. So that's my equilibrium or steady state solution. So let's say if I find this, I would like to know, when does this happen? So with which rate, right? So I start my whatever with initial conditions, and when I reach the equilibrium that I'm interested in, I would like to, if possible, quantify that, like which time I will be having that. And another problem that I can look at is the stability of solutions. I can, for example, perturb my equilibrium and check what happens until which perturbation I lose the equilibrium, right? But these are the general problems that I would be looking at. And now I would like to tell you a little bit about the differences between the kinetic equations coming from applied sciences, like run-and-tumble equation, and kinetic equations coming from gas dynamics. So first of all, the first equation I showed you, these Newton's and Newton's equations, they were fully deterministic, right? If my interaction potential was good enough, I would find a unique solution or a unique flow. It was a Hamiltonian system. But in this case, for run-and-tumble and in general models coming from sciences, that applied sciences, I have stochasticity involved. So I cannot find a solution. I cannot actually carry out this limiting process as I described you in the beginning. So like also, again, if you have seen 2 weeks ago's talk, that there was a mention of time reversibility. So stochasticity does not allow me to have a system which is time reversible, right? So second one is that I mentioned that one of the assumptions that I made was conservation laws, right? For these models coming from sciences, again, for run-and-tumble, for example, I don't have conservation laws. I don't have the conservation of momentum or an energy, let's say. So there is a conservation of mass, but it's not enough sometimes for me to carry out my analysis. And the third one is the steady states. We again, it was mentioned 2 weeks ago, the steady states of these kinetic models in gas theories is a Gaussian function in velocities, Maxwellian velocity distribution. In this case, I don't have that. I don't know how, if there exists a steady state, and if it exists, what is the shape of it? I have no idea, right? And the fourth difference is the confinement mechanism. So this, I didn't mention so much the Boltzmann equation and the equations in gas theory, but the confinement there comes from the external potential. Whereas in this model, for example, confinement comes from the bias in the velocity. So it's a different mechanism. One of them is external, the other one is internal. So why I am telling this is that because of these differences, some well-developed theory for kinetic equations in gas theory does not apply to the equations, kinetic equations coming from applied sciences. So we need to invent new methods to be able to study these problems, right? So this is the last slide about the run-and-tumble, where I summarize what we did in these papers. We looked at a linear version of this run-and-tumble equation for bacterial movement, and we could prove the existence of a unique equilibrium, and we could also show the exponential convergence to that unique equilibrium. And we introduced some weakly nonlinear version of that model. That means that it's nonlinear, but the steady states are the same as the linear one. So it's kind of a small perturbation of the linear equation. And in the second paper, we look at the non-uniform tumbling kernels. And I told you that the velocity space was like a ball. Here we look at the unbounded velocity space. Again, we could show the convergence to unique equilibrium. So for example, in the unbounded velocity space, this convergence is algebraic. It's not as fast as exponential. And we use some tools coming from probability. So I will not go into details. So this is more maybe if there are people who are interested, I'm happy to talk about this. So this is the first example that I would like to give. And the second one is one of the recent works, which actually was completed a month ago. It's in a collaboration with Sarah Merino. She was my postdoc supervisor in Vienna, and Claudia also is in Vienna. Stefan Plander, he's in Kyoto, was visiting me here end of August. There we could finish this. And this is about alignment interactions of elongated particles. So imagine you have a tray and it's filled with basmati rice, and you shake it a bit. What you observe is that in time, these basmati rice grains, they get aligned in this way, right? And this you observe in different, of course, configurations where you have these type of elongated particles, right? So another example is from biology. This is the fat tissue. Here is the pictures from, I guess, real fat tissue, and this is more detection of it. And here you can see also in some bacteria colonies how they get aligned. So how I define, there are other applications, for example, liquid crystals, and some applications from molecular dynamics. So this type of alignment, I call it nematic alignment. So what it means is that you don't distinguish when the particles get aligned, they don't distinguish head and tail, right? So if I take two unit vectors, so they are nematically aligned if their magnitude up to a sign is equal to each other. So you cannot distinguish which part is head, which part is tail. So this is a nematic alignment. So what I would like to do is to write a mathematical model describing this type of alignment, okay? So this is what I do. So I would like to consider n particles of this shape, and I identify them with their centers, x1, x2, let's say xi, and with their directions, which is the direction of their main axis, longer axis, L, smaller axis is D. Okay, so I say that this type of behavior can be modeled with this stochastic differential equation system, where I see in the first one change in the centers according to some interaction potential VB, which depends on this show, yeah, depends on the directions of two particles and the distance between the centers. And as I mentioned, there is stochasticity involved, and it is modeled by Brownian motion here. So there are a lot of letters, so I'm sorry about that. It's not very, you don't need to focus on those. So these are all positive constants, mu and d, which are, they are like describing the intensity of these potential force and let's say randomness. And similarly, change in the direction, I can model it in this way. And here again, I have the interaction potential. And what you see, the particles, they are going through the steepest descent of my potential. So where it decreases the fastest, right? So that's why there is a gradient here. And again, I have the Brownian motion randomness in direction as well. So here, this projection operator, it's keeping, since my directions are taken from sphere, this is keeping that, like taking care, making sure that they remain in the sphere, this type of projection. So here, what is important is that this interaction potential, so here I'm using soft potential, let's say. So I'll come into details, but what I would like to say, the particle anisotropy, which means how elongated they are, matters in this case. So here, for example, this chi will be describing how elongated the particles are in 2 dimensions. Chi equal to 0 means I'm looking at perfect circles, and chi equal to 1, I'm looking at infinitely thin rods. So it's in between the ellipses in 2 dimensions. In 3 dimensions, it will be chi will be from -1 to 1, and then I will look at spheroids, but I will not consider in this case. So why I said the potential is important, because depending on, so again, this is not very important. What is important here is this scaling parameter, determinant of some matrix which involves my anisotropy. So it depends, like, so if I take different values of scaling, like the different scaling, I observe different things. For example, in the first one, I don't observe at all nematic alignment. So I cannot take that potential if I would like to describe this dynamics. So what I'm gonna take in this work is the last one, which I call as weighted Gaussian potential, where I observe nematic alignment. So let's briefly look at what the particles do. So under this dynamics, I simulate these particles here, color. These are all small ellipses, and the colors represent the direction. So different color means different direction. So pink ones are all same direction, green ones are all same direction, but they are different than each other, right? So what you will see here, time 0, and this gamma f is the order parameter. So it's 0 means, or it's very small means, they are not aligned. And when it gets higher, you will see the global alignment, right? So this is what I would like to find, nematic alignment. So these are the parameter values, which are not very important, but I just put for the sake of completeness. So if I run the simulations, what I see is that, see in time, they get aligned. So they kind of get to a uniform color. That means that they're really nematically aligned. So it's like, it looks like the model that I propose is a correct one for this type of behavior. So what we were interested in this work was to derive a kinetic equation for this, and then macroscopic equations, like particularly an equation for the mass density and equation for the mean nematic orientation. And okay, I will not probably go into details here. What I wanted to say is that the equations are these, they look ugly, which is expected, but what is important is that we found some condition, which is for well-positance of these macroscopic equations, and they correspond to these red lines. Here are heat maps, where there is 1 means that they are ordered fully, and 0 means that there is no order, like they are not globally aligned. And here some constants in front of the Brownian motions in x and direction u. Here is the lambda and mu. These are the intensities of my potentials in X and again direction U. So here, what I wanted to say is that this well-positiveness condition that we have for the macroscopic equations in the microscopic level, we see that actually if I'm not in the well-posed regime, that I don't observe any kind of nematic alignment. So I always fall into this part. So somehow in the macroscopic and microscopic models, they are in agreement in this sense. So I also wanted to mention a little bit of particle anisotropy. So here you see again a heat map. How to interpret this is that, so here the red lines are my anisotropy parameter. So above it is like 0.4, it's like more circular. So I could also go extend this up to 0, where I would have the perfect circle. So in that case, with the low densities, these are the density lines, I don't obtain any alignment. So I wanted to show you with this simulation where I believe the anisotropy parameter chi is 0.7. So they are more spherical rather than elongated, less elongated, let's say. So I'm in actually somewhere in between and somewhere here probably. And what I will observe in the same time is that the alignment looks like, I mean, I don't see any global alignment, little bit locally here and there, but I don't obtain alignment at all. So yeah, this was the second example. And there's the last example, but I believe I won't have time for that. So if you're curious, this is another very different thing in social, rival gang interaction, but yeah. Thank you very much. So I go to my last slide so that you can also see this a bit. Yeah, thank you very much for your attention.
Thank you very much for a very nice talk. So, questions?
Yes.
Hi, thank you very much for your talk. It was super interesting. And it's kind of complex, so I'm not sure I'm understanding things correctly. But in your nematic alignment model, you have like a temperature sort of parameter?
Sorry, which type of parameter?
Like a kind of like a temperature in the Ising model or something which controls the amount of randomness, like thermal fluctuations?
So you mean maybe the constant in front of the Brownian motions?
Yeah,
exactly. So intensity of Brownian motion. Yeah.
So do you observe any phase transition like transitions in the system?
Yeah.
Depending on temperature or like depending on
yes,
density?
yeah. I do. So it's very okay. Sorry. So this graph precisely, I tried to show that a bit. So here, for example, these are the precisely what you asked for. These are the constants in front of the Brownian motions in X and U. And like this is the global order, right? The order, like here, this means the yellow means they are ordered fully. And this means they are in chaos, they are not ordered, right? So what we observe is actually this well-positiveness line for the macroscopic equations is that, like, if you are below that, if you are not well posed, the microscopic dynamics also does not, it doesn't reach any type of global alignment. So this is one kind of maybe phase transition. It's so theoretically, I mean, I think there are some more, but it is difficult to somehow guess theoretically. Then we cannot also find it numerically, right? We need to kind of look at the parameter like
the divergence of correlations and
sorry,
like divergence of correlations or divergence of susceptibility, something like this, to determine what happens.
Well, I don't know what these things are, but we I mean, this one we looked at this line because we knew that from macroscopic equations we will have this well-positiveness region, and that's how we could say that, okay, let's do these parameters that in the microscopic sense as well. But from maybe there are, as you said, there are some ways of defining these phase transition parameters one can look at. So I don't know that so much yet.
Okay, thank you very much.
Thanks a lot for the question.
I work in fluid mechanics. So I'm just interested to know whether the well-posedness condition like this and the turbulence, all these things, can you comment on all these things? Like, can we say something like similar to this fluid mechanics equation, Navier-Stokes equation?
Yeah, so I think Navier-Stokes equations are more kind of well understood. So I can just comment on this case, not well understood in the sense that, of course, turbulence is a very complex thing. It's not, I mean, that's not what I mean at all. What I mean is that you probably haven't seen an equation like this because it's kind of coming from a system that we made up, right? Like, so the well-posedness condition purely coming from this part. So if this term is negative, then the equation does not make sense. It will not have any solution. So it's very kind of maybe simple way of finding a condition. So for the Navier-Stokes and stuff, I mean, it's not as complex as those, let's say. I mean, maybe this is also complex, but at least this is our simple understanding. So yeah, I don't know. I cannot relate it to turbulence or these kind of things. I don't know them very well. Yeah, but thanks for question. Yeah.
Any other questions? Yes.
That's very nice to see that there's a mathematical tool, systematic tool that you can go up in the scale. I'm curious, is there any attempt to go down, like from macro scale
to micro scale? I don't know. I don't think so. We always try to go up, right? So there are also ways to go directly from micro to macro without like skipping the kinetic, or quantum to macro, let's say, or quantum to kinetic. But I don't think any. Yeah, I am not aware of if there is any. I don't know. Yeah, that's an interesting question. Yeah.
For these elongated particles, this doesn't have any uses, but you mentioned the 2D and 3D. Does the theory generalize if you have like a 4D particle that is elongated in one direction?
Yeah, so I think we cannot simulate that, but also the derivation of equations that we did, they are not valid for this. So it's just for 2 and 3. And for 3, it's a bit more complex. I wrote these equations in a more simpler way. But yeah, I think there is some theory to develop for these to be valid in 4D.
Okay.
Yeah, thanks.
Other questions? I have a question. So, I mean, first of all, you call this equation ugly. I find it quite pretty.
Yeah.
You have two diffusion terms.
Yeah.
And then you have linear diffusion, classical diffusion, and Boltzmann.
Yeah.
The combination.
Yeah.
Mu is a kind of the parameter.
Yeah.
So, well-posedness condition when dx over mu becomes from the constant second term bigger than du over lambda. So what's the du? Remind me.
These are just the constants in front of Brownian motions in U.
That's stochastic.
Yeah, it's stochastic. Yeah.
So what do you mean by well-posedness? What is proven? Existence, uniqueness?
No, yeah. So that's a very good question. So yeah, these are open. So that's not what I mean by well-posedness. So the one I described, existence, uniqueness, and stuff. So well-posedness just in the sense that these equations physically won't make sense if you are away this parameter regime. So these equations kind of, I guess, too complex for us to say anything rigorous. So this paper is kind of a bit formal derivation, not a rigorous derivation. And yeah, like you said, the first one is nice because, as you said, is linear diffusion and nonlinear diffusion. And what is interesting is that the evolution of density is independent of the mean direction. So mean direction, mean orientation has, like, the density has an effect on mean orientation, but mean orientation does not have any effect on the density. So this is something which we find surprising. And this K term is smaller than 1 always. So for 1, it is like a Frost medium equation, right? And that's why it kind of gives you like slowing down the diffusion effect as the particle shape changes. This depends on this chi parameter. Yeah, but this well-posedness is not in the sense of like classical well-posedness. So.
The numerical simulation which you did, they demonstrated that we need this condition.
Not exactly. It's just because of this term. So this term, if this term is negative, sigma minus nu, which is exactly this and that, right? And when this is negative, this equation will not make sense physically. Yeah.
But was there any attempt like just write this as a one diffusion, only diffusion when coefficient will just kind of. But what happens, like for example, if you have a second force medium, if you have a degeneration, no diffusion, but then classical diffusion will still push it to infinite singular propagation. I don't know, and then vice versa, at least from them.
Yeah. So the thing is,
very interesting model. So is there anything known about this model, like results, like mathematical results, existence?
no, this is it does not exist for this model. But for this one, for example, first equation, you can see that this first linear diffusion comes from the Brownian motion, right? And the second part is coming from the interaction potential. So of course, if you take a different potential, you will have different nonlinear diffusion. So that's maybe related to what you're asking. So it also depends which type of interaction you would like to observe, right? So for some scalings, we don't see any alignment at all, right? So yeah, it's
derivation of this model is purely empirical, right? So is there any connection you have to diffusion processes? Do you have any process where this will be generated? I think this will be interesting.
Yeah, that's indeed. Yeah, on top of my head, I don't know. I cannot say. Yeah.
Something Brownian motion, but different.
Yeah.
If you remove this diffusion, like non-linear travel, I don't think there's a probabilistic meaning. There's no any process like the force. Brownian motion has clearly this diffusion, so it's nice to see if this combination
makes sense.
Kind of probabilistic.
Yeah, you're right. Yeah, that's a very nice comment. Yeah.
So the well-Poisonous condition only affects the second equation, and the first one we don't see any.
No, you don't see because I did not explain. So this equation is valid only when rho is above a critical density. So it appears here in the second one too. So yeah, so these are connected through this critical density. So and that comes from the collision operator of the kinetic equation, where you look at the stable current, like stable equilibria of the collision operator, and you observe that if you are above from some critical density, you have equilibria, and if you are below, then you completely go to isotropic regime, where like you don't have any elongation of particles and no second equation, let's say.
But if I just look at the first equation by itself, there's also a well-Poisonous condition or not for that one?
Yes, it has. Yeah, there's which I did not write. There is a well-Poisonous condition for that. Yeah. So this second equation is valid under the first equation is valid also, right? So once first one should be well-posed, like valid, and then the second one also applies. So this second one depends on the density.
Yeah, but for the second one, I can see that if the coefficients have the wrong. I mean, if nu is bigger than sigma, there's a problem. But for the first one, it's not less obvious, right?
Yeah, it is less obvious because when you are in low density regime, this k term simplifies.
Okay.
And it becomes something else. So it becomes like just an equation for density. And for that density regime, you don't have the second equation at all. So there is no alignment or anything. So it's kind of makes a connection to purely spherical particles. They don't align, right? So you don't observe any alignments, and you just have an equation for density evolution. Yeah.